This is a tutorial on how to run the ImmunoNX pipeline. Really, all I'm going to use is this GitHub repo for the instructions, which has pretty much everything you need to get set up and get started. The README that we're going to use is the running pipeline README. And I'm going to demonstrate this with a completely new Google Bucket account. The example data set is this HCC 1395 cell line, well-known breast cancer cell line that can be purchased and is commonly used for benchmarking. They have realistically deep sequence exome and RNA-seq data. And the pipeline performs QC, germline variant calling, somatic variant calling, HLA typing, RNA expression, and neoantigen identification. Okay, so now we're going to move into setting up our Google Cloud account. So I'm at the Google Cloud webpage over here. I'm going to click sign in, and I'm going to use my spam email account to do this. Hopefully it has my password saved. Okay, so you get $300 in free credits for a new customer, which we are going to utilize for this. So hopefully we can test this without, or we will be able to test this without paying actual real money. Okay, so here we are on the dashboard now. And it shows you your 300 credits. It also shows free trial status, 300 credits for 90 days. Activate your full account to get unlimited access to Google Cloud. Use any remaining credits and pay only for what you use. Later, we're going to select activate because we're going to have to request increases, and I don't think you can request increases without fully activating your account. Okay, so we have my first project. You can create a new one if you like a newly named project if you want, but we can just use my first project. And we're going to go to buckets to create our storage bucket. Create. It's going to give you a lot of options. And we're going to say ImmunoNX test. Oh, underscores. Only lowercase letter. All right, sorry. Okay. So geographic location of the data. And we're going to click US. And yeah, that's what we'll choose. We'll basically set everything pretty basic. Make sure it's not publicly accessible. Okay, now we have our storage bucket. We don't need the tutorial. And as you see, there's nothing in it so far. Oop. So now that we have our bucket set up, our account set up, let's hop back to the README. And we're gonna follow these setup reminders for new users. So first we're going to set our project ID. So right now I'm in a folder ImmunoNX test. There's nothing there right now. We're going to see what projects I have access to. And first I need to log in, which should be pretty easy. You'll open up this page. You click your Google account. You authorize everything. Okay, cool. And now we should be able to see our projects. And yep, we just have that one, my first project, with project ID and project number. And then we're going to set our project, which will be using the project ID, not the project name. Then we can also set it as an export, which we'll think about doing later too. And then we can verify that it's set correctly. Cool. Okay. And then we have to link our billing account. Because even though I think we entered our information we still have to authorize the billing, and maybe this is when we'll have to activate also our account fully. Get an account. Yeah, it looks like it's changed. I don't have it. All right, let's activate. Project's linked. Maybe it's already linked. We will see if we get an error later. Okay, but while we are over here, might as well set a monthly budget and make sure that we do not go over our $300 free credits, because that would be not fun. We'll have all projects, all services. It should only take around $50 to run and store all of the information and all of the like pipeline processes. So $100 should be plenty. Okay, now we have a budget. Let's see if billing and label enabled is true. You have to install this beta command. Not enabled for the project. Oh, billing enabled true. Okay, cool. Okay, and then we will enable the APIs to allow the project to orchestrate virtual machines. Okay, operation finished successfully. And then we can make sure that it works. And it's going to give you all of the current metrics for your project, which the next step is we're going to request some quota increases. So we're going to go to IM. An admin. And then we're going to find quotas and system limits. Okay. And the default CPU should already be at 200. Okay, so using this is really fun. You type in CPUs and then you scroll to find just the normal CPUs. And then we specifically want to see it in our location, which should be US Central. Okay, wait. Just US Central 1. Okay, yes, and it's already at 200, so that one's good. Okay, now the preemptible CPUs. Name preempt. And right now the value is at 0, and we're going to do edit quota, new value, 100. And then this is submitting a request that should be approved pretty quickly. At least when I tried this the first time, it was. And the request has to be approved. Okay. Let's do the next one in use. IP addresses. Right now we have 8 and we would like it to be 25. Okay. And then the persistent disk. So the persistent disk request might not be necessary. This like 10,000 gigabytes is a pretty excessive amount. Right now we have 250. But let's see if we get approval for this. Actually, we're not going to request this one because when I ran it before, it worked just fine with 250. So we'll do the test again without the persistent disk increase. Okay, so now we have our 2 increase requests, or only one showing. And that was already approved. Oh, okay. Oh, approved. Cool. Okay, so they're both approved pretty much automatically. Great. So now we're going to, there's some notes about setting the IP address, which we might come back to, and also setting our compute zone. So let's do that too. We're going to use US Central because we are in the middle of the US. Property validation for compute zone. Skipped, updated property. Okay, we'll assume that the property has been updated. Okay, so now we're getting to actually setting up the pipeline. And we've already played a lot with this project name, which we'll pull again. But we're actually going to make a environments file to hold everything else, just so it's easy if we have to come back to it and reactivate our environment. So we'll go ahead and paste these here. Oops. And I have the Finder window open down here for a better visual. And we will follow the instructions. And add our own project ID. Okay, our service account should remain the same. Our bucket name is not this because I should have named it that, but I didn't. Okay, let's go back to our bucket. Please, this one. Okay. It's ImmunoNX test. Okay, bucket path will just be the same path. We'll call our sample HCC 1395. The instance name is going to be the sample immunotest. That can be whatever you want. We'll get our working directory, which is here. We don't need that little tilde at the beginning. And we'll put our raw data here, theoretically. And then our workflow definition is going to be defined in this Git repo that we're going to, or this Git folder that we're going to clone repos into, and then the name of our local and cloud YAMLs, which we'll make in a bit. Okay, so those all look good. All right, source our env, our environment variables. Okay. So local setup. So we could create the working base that we defined and CD into it, but basically we're already there. There's nothing in it but our env's text files right now. Okay, and then we're gonna make a Git directory and clone a few Git repos in it. I'm gonna just copy and paste these, and while they're cloning, so our first one is the Git repo that we're in right now, the protocol Git repo, which will have our example YAML file in it. And then we will also have our analysis windows, which is actually going to be the repo with the workflow definition in it. And then we have our cloud workflows repo, which contains a bunch of helpful scripts that are going to help set everything up and make it really easy to do that. Okay, so we have those 3 repos there. I'll make it a little bit bigger, but not to mess up our setup. Okay, so we logged in already. So we don't have to run it again. We can, I think it will just make us do the same thing. Yeah, open the account, you authorize everything. Okay, we're authorized. And then we set our project, which we also already did. And then we can list our configurations. Yes, we're in the US Central Zone. This is my spam email. And then our project. Okay, we're moving. So now setting up the cloud service account, firewall settings, and storage bucket. So we're going to run this resources .sh command, which lives in our cloud repo, cloud workflows repo that we just cloned. And it's going to make sure that working.in exists and that the bucket exists. And it will create some Cromwell configuration files for us. Oh, okay, and now we're at this like IP thing, which we have a note of it here. So you can either, going back up to these directions up here, notes on IP address things, we're just going to use this like IP 000 for like allowing anyone to access in the allowing anyone from any IP address to access the VM we're creating. Obviously, for more security, you can set the IP address to just be the Wi-Fi that you're working on. And you can also add different IP addresses in the Google Cloud bucket for security reasons. But we'll just use, I'm not really too worried about our test run. Okay, so now everything is set up and getting ready to go. The next step on the README is downloading the input files for HCC 1395. I know that on my personal laptop, which is what I'm running this on, I don't have enough space. So I'm going to deviate a little bit from this README and actually download the data onto the VM that we're going to create in the next step. Now, usually what this would look like in the download data files would be like wherever you're working on your like institution's compute structure, you'll have your raw files that you want to run, and that's kind of what this is simulating. But since I don't have a lot of space for these big files, I'm going to just download them onto the VM and then actually upload them to the bucket to use the cloud storage in this instance. So we're skipping to start a Google VM that will run in Cromwell and orchestrate the completion of the workflow. Again, in our cloud workflows, we have a really nice command that's going to just start this for you. And we already defined our instant name, our service account, the project, and everything. And we're going to give it 250 gigabytes, which is great because that's where I'm going to keep all the files when I download them. Yeah, and it gives this warning that maybe 250 is too big. You might not need that much, but it's a comfortable amount, so that's what we use. And then you can SSH into the VM using this gcloud compute SSH and then the instance names, which is right here. We also have it stored in this environmental variable. Okay, so now as indicated by this green text, we are on the VM and there's nothing there yet. And if we go ahead and run this command that's going to show us our startup script, we see that it's starting up everything. And eventually it stops. And then if we look at the journal, okay. So now that we have the VM set up, I'm going to go back to downloading the input files, and we will make a directory to hold them. And then we'll wget this tar file. This does take some time. Okay. So we got the normal. Now we're gonna untar it. And it's gonna open into the two pVACview files. And I'm going to add some stuff into our bash RC, and by some stuff, our bucket path and our project are most important right now. Again, just doing this for ease because Okay, so locally, we are going to take a look at the references stored in the Griffith Lab Google Bucket. There's also this guide on how to make your own references, which might be necessary to do for some projects. Again, since this is just a test example, we're just going to copy the human reference from the Griffith Lab bucket. So we'll copy the human GRCH38 Ensemble 105 reference, and we're going to copy it into our bucket at into this folder that we'll create. And now we have all the reference files in our bucket. Woohoo! Now we'll go back to downloading all of the HTC 1395 files. We're going to log back into our VM. We have downloaded all of the data to our VM. Our pVACview files located on our VM. And now we're going to make our YAML file using the locations of those pVACview files. Okay, we downloaded our input files. Here we have them. And then we copied our reference files to our bucket. Here's our bucket over here. We can look. Here's our reference files. We see them here. I can actually close that. So we're at our working base because we defined our environment variables in our env file. So here's our working base. We'll make a directory called YAMLs and then we'll cd into it. And then we will take this example YAML located in the ImmunoNX protocol GitHub and copy it into our YAML folder to work from. So just copying an example, we'll see it in a little bit. And we'll see it down here, template immuno YAML, and then we'll move it and we will call it our local YAML. So there we go. Now it's the HTC 1395 immuno local YAML. All right. Let's open this with a text editor. I'm going to open it with Visual Studio Code. Here it is. So we see that we have to fill in our pVACview paths. And also our path to our reference folder. So let's start with the reference folder. That's pretty easy. It's going to be the path to our folder here on our bucket. So we can actually do it two ways. We can copy it with that little copy symbol, or we can, no, we can't do it that way. Okay, we'll copy it like this with that little copy button. And then we will do a find and replace. So now we see that all these reference files now have the path to our bucket where the reference files are located. Cool. Okay, so again, we're pretending that these files would probably be located on some local server that you have that has more storage than my personal laptop. So we'll start with the tumor sequences. So we will say, we'll go ahead and change directory into the tumor exome. We see our pVACview files. Okay. So yeah, we see path to the tumor DNA, read one file locally on laptop or server. Grab our read one. This one will be our read two. Okay, so and our ID can be tumor DNA. Flow cell ID, we don't really know this, so we can just leave it blank, or I'll put in a 0. The sample name can be also whatever you would like. We'll call this tumor DNA. It just has to be the same as the sample name here. It should probably be HCC 1395. Tumor DNA. Making sure it matches our sample name down here. Library, we can just call it this. Library 1. Sequencing platform. Also, this is information that if you know, it's helpful to put, but it's not required. Just put 0 for both of those. Okay, now let's do the normal sequence. Okay, so that's how you set it up. So now I think we have everything. You can input if you have clinical HLA typing, you can input that here. We're also going to leave that blank. Okay. So now we have our YAML file. So now we stage input data to the cloud bucket. The reference and annotation file should already be in our bucket. Good. However, the input pVACview data files are still only on your local system. So we need to upload them and update our YAML file to point to their new locations on the cloud. So we're going to start a Docker session that is going to allow us to cloudize our scripts. So it's going to basically copy the files that are located locally, in this case on our VM, up to the cloud, and then create a new YAML file that has the cloud paths automatically in it. Okay, so the file upload completed, and we see them now in our bucket. And we also see that it created a cloud YAML for us. Oh, and it called it a YAM instead of a YAML. I think that there was probably a typo in our environmental variables that we set. But if we take a look at it, probably better to do it this way. We can see that it now replaced our local paths with our bucket paths, and it reflects where the files are located in the bucket. So it looks like it worked. We can exit out of the Docker, and we'll probably rename our YAM file to a YAML file. Oops. Okay. Move. Okay. So now we have our YAML, we have our VM. We can copy our cloud YAML to our bucket. Now we are at the run Immuno workflow using everything we set up so far. We're in our home directory. So we are going to source some of our helper scripts that were automatically installed into the VM. And then all we have to do is run the command submit workflows, which is located in helpers.sh, using our cloud YAML script. Okay. And it should say submitted successfully. And keeping this ID in mind, that is the workflow ID that it's going to run under. We can monitor the process of the workflow using this journal control -u Cromwell. And we see that it's parsing the workflow that we provided it to it. And soon we're going to see that it starts the task. Or here is where, if there's a syntax problem in the YAML, it will yell at us and be upset. But see it, we see starting sequence to BQSR, sequence line and tag. So it looks like it's parsing the YAML well. It's adjusting some CPUs. And starting, our Cromwell is starting a bunch of different jobs on different VMs, which are running these individual tasks. If we take a look at our bucket now, reload, we now see a Cromwell executions folder with that same workflow ID. And we see it started the first task, this is in the way, call RNA, and it's starting the RNA seq star fusion step. And it says status change from, from blank to initializing. So it's initializing the task, and soon it will say that it's running. And so you can both monitor the workflow by seeing where it is in the log file. You can also get some sense of where it is by looking at the bucket and what outputs it's generating. And this run will take about 2 days to complete. So you can check it periodically to see if it encountered any problems. But all in all, it'll take around 2 days to complete. So now we just wait. Okay, I'm going to log in and check the run status. And if I just use the journal control command, and I see that workflow has failed. So this happens often, that you get a failure, and usually it's due to a user error making the YAML file. And so immediately I see failed to evaluate reference size and then file not found. Okay, so this reference file is not found, and immediately I see what the error is that the file path is repeated twice. When we know that that's not the correct file path according to our bucket, it's just one human and then here. So error in the YAML file that we will have to correct, and then it will continue. Another error I recognize is that we didn't set the strand. So here you're supposed to select first, second, or unstranded depending on your data. This is first strand data for us. If you don't set it, the pipeline doesn't fail. It just assumes that the data is unstranded, which could result in not as clean of alignment. So we'll fix the reference path. Okay, now the YAML's fixed, and then we can resubmit the workflow with that YAML. Okay, so now we're going to look at after the pipeline is finished running. I'm switching to another run from another bucket that I created, a different test run, but the same principles will apply, and the steps after the pipeline is completed running are pretty simple. So we monitored the progress of the workflow using the journal control command. At the end, it should give you a failed or succeeded status. If you don't see either of those, it's still running. And what that looks like is demonstrated here. It's a little hard to see, but it will have completed with status succeeded. And I'll also put right here what that looks like in the terminal for this run that I'm going to show you. So once you see the succeeded status, you can now pull all of the outputs. So we move to the next section, save information about the workflow run itself, and this will give you the timing diagram. This is how I knew how long in overall that the pipeline took to run, and also gives you some other useful information for seeing how long some tasks took. So I'll show a video of me doing these steps, but if we look on our bucket, we can actually see in our Cromwell executions Immuno folder that we have all of our workflow IDs here in different folders. And a completed workflow will have all of these different folders in it calling the different tasks. These other ones that are in here are incompleted, failed runs, probably due to YAML failures. But this one is the correct one with all of my completed outputs in it. So if we look at one of these folders, like our pVACseq folder, we see there's like a lot of nested folders in it with a lot of nested tasks. So the pull output scripts is going to pull the specific outputs that we want. So we don't want these scripts that are running the task or these log files, but we just want the main output from that task. Or sometimes we don't even want an output from a task. We want the ending output after all tasks are complete. And then after you save the workflow artifacts, get the outputs.json file, then you can enter a Docker and then pull actually the final results. And the final results folder will look something like this. I have it uploaded to the Google bucket. You probably will want to pull this somewhere that you can store it locally, because again, you're paying for storing things on the Google bucket. But this folder is kind of big, especially the cram files are in the gigs, and I tried to download it to my local laptop, but again, I ran out of room, so I only got a few of the folders, and I think when it started trying to get the cram files, it was like, I'm out of room. But we have some of the outputs here, but the full outputs you can see are in this final results folder. If you pull, when you execute pull outputs, this is what the file structure will look like. And then you can examine the outputs and then estimate the cost, which will give you those final stats. And then once the workflow is done, and your final results are retrieved, you're going to destroy the VM to make sure that you are, again, not paying for that anymore either. So the last thing I'll show is opening pVAC. So I'm going to go to pVAC, seek, MHC1, and we'll open the RShiny app in our RStudio, which looks like this. And then if we run app, it will open in a web server, the pVACview interface, and then we can add our files to view our neoantigen candidates. We'll add all isotypes aggregated, the aggregated JSON file, and then we'll also add the class 2 predictions. We'll call that class 2, and if we had a gene of interest list, such as cancer driver genes, then we could upload a TSV here, but we don't need to. And then we see our candidates. So the results of that pipeline run are displayed here. I hope that this video demonstrates that a lot of work has been done to make sure that this pipeline works seamlessly and can be set up easily to run. Some pretty computationally intensive tasks, as demonstrated by how long this takes to run. But actually it's pretty easy to get started and running and to verify your results once the pipeline is done. So thank you.